Hello and welcome to Disseminate the Computer Science Research Podcast. I'm your host, Jack Wardby. Today we have another installment of our Slider series, and I'm delighted to say I'm joined by Suyash Gupta, who will be talking about his paper, Chemistry Behind Agreement. Suyash is a postdoc at UC Berkeley, and he's currently working on designing efficient fault-tolerant systems with a key focus on handling malicious attacks. Suyash, thanks for joining us on the show.
Yeah, thank you for having me. I mean, it's great to join here. This is an exciting platform, and I think it will help a lot of community. As I'm doing a postdoc at UC Berkeley, this was a recent paper which we presented at Cider. So I'm excited to explain it and look forward to any questions.
Awesome. We're happy to have you as well. So before we get into the paper, can you maybe tell us a little bit more about yourself and how you became interested in researching databases and distributed systems?
Yes, I think so. I have been starting to do database research, I think, from Purdue, from where I started my PhD, and then I moved to UC Davis, where I graduated. So I think we were taking a course which was looking into designing commit and concurrency control protocols, and that sort of intrigued me in like, how are these protocols designed? Can we actually do something new? And that's where I started to take a deep dive into distributed databases. And interestingly, this work is sort of a extension to the early days when I started doing that, because back then when I was looking at how to design two-phase commit protocol or three-phase commit protocol. And then I soon moved on to doing consensus protocols, basically fault-tolerant consensus protocols. So this work sort of takes care of all of those protocols and tries to bring a single framework in some sense.
Amazing, yeah. I mean, concurrency control, right? That's what got me hooked as well. So, yeah, that's definitely like the gateway drug for databases. Maybe, I don't know. Yeah, cool. So you touched on it a little bit there as sort of the general idea behind the paper, but can you maybe give us the elevator pitch for this work?
Yes. So, if I have to say that, I'll say that out in the wild, there are many type of agreement protocols which come in several flavors. Like commit protocols are there. There are protocols which can handle crashes. There are protocols which can handle malicious attacks. But despite this, we believe there's no single framework which can express all of these protocols. As a result, what we feel is that there is a disparity in understanding and usability of these protocols. And such a disparity kills innovation and adoption. In fact, in just this cider, we were listening to some talks and we were listening to people discussing among themselves. And a common framework statement was like, PAX was hard. So still there is what people feel not easy way to understand this protocol. And that is where our work come into picture, chemistry behind agreement. We try to design a chemical framework. Per se, it's called as chemical, but the idea is to design a framework which can express all of these protocols. And the hope is that using these frameworks, developers can come up with new protocols and they can actually adjust the system based on the requirements.
Yeah, I mean, it's super useful work. So I know from personal experience, trying to understand all the different variants of Paxos and the whole spectrum of protocols there, right? It's so hard to compare and get your head around each one, sort of teasing out what the primitives are and things. So yeah, definitely really sort of helpful work on that front. So you've I really like the chemistry angle to it as well. I think that's a really good way of thinking about these things. So you start off by in the paper by defining like 4 atoms. So can you maybe run us through each one and why you decided on these 4 being the 4 atoms?
Yes. So the idea behind this paper was like, if, as you just said, we're trying to say what is chemistry. And if you're saying chemistry has main elements, things. There's something atom, there are elements, and then there are compounds. So first thing we need to design is what is atoms. And in chemical term, atom is basically the smallest indivisible unit of an element. So similarly, we were trying to think, what are the atoms of different agreement protocols? How will these protocols actually come into being? So I think few things which you realize that all of these protocols have something which is called as a failure model. Failure model means what type of attacks or things they can handle. Like, for example, some protocols can simply handle crashes and they cannot do anything more, and that is good enough. While some protocols can actually handle Byzantine attacks or malicious attacks, and that the replicas could actually collude, they can lie or do anything else. So first thing is we need to define what is the failure model. Next element according to us is quorum. Basically, if we are designing a protocol and in that protocol there will be multiple parties, what is required from these multiple parties to come together and reach a common decision? And that is what quorum basically tries to tell. For example, in some protocols, the idea will be that you need all the parties to come together. So in a system, if you have n parties, all n of them should come together. While some protocols will say, hey, I do not need n of them. I only need a subset of them. And that subset could be F. For example, Paxos style protocol, what they say is that if you have n parties and they say that n is equal to 2f plus 1, then I only need f of the parties to come together, reach a common decision as f plus 1 parties. And that is the quorum for them. Similarly, in the BFT world, but the idea here has been that a lot of protocols say that we need two-third majority, so 2f plus 1 to come together and actually reach a common decision. So that is quorum for us. Then another element we thought is that, okay, we have defined failure, we defined quorum, what can we do next? The next thing which we thought is will be topology. Basically, where will these protocols run? How will these protocols run? So generally, if we say in the broad outlook, the protocols can run either as a centralized setup or in a decentralized setup. In a centralized setup, the idea will be there will be a leader which will actually initiate the protocol and everyone else will follow whatever the leader is saying. While in the decentralized setup, everyone can work together and they can send messages to each other, they can communicate with each other, they do not need to wait for the leader to initiate stuff. Alternatively, we also there are some protocols which follow a ring design where the idea is that I will just communicate with two of my neighbors. Basically, we assume a ring like structure, everyone is sitting in a ring and they are communicating. So these are some of the sort of like topologies we see are common. And finally, the fourth element, which we thought is like a data distribution. How is the data distributed among these parties? Because we have these parties, and what are these parties actually holding on to, or what are they actually executing? So one way could be that all the parties are holding exactly the same data, and that is a common replication model. While the another scenario could be where every party only has a distinct set of data items, and traditionally this thing is called a sharding. Similarly, there are some models which use flavor of both, where you have both sharding and both replication happening at the same point in time. So this is what how we define generally the atoms in the system.
Nice. How did these four things sort of come like fall out then? I mean, was there certain other atoms you like, do we make this an atom or not, or was it pretty obvious from when you started to trying to decompose this and break this down that these were the four sort of founding like indivisible atoms, right? That kind of fell out.
So that is again a very good question. I think why we thought about only these four atoms was the reason is because we saw a lot of different protocols, and I think some of the protocols which we'll be discussing later in this podcast also will be that any protocol which we have will follow some of these structures. They will first define how their party should have the data. They will, of course, define what is the type of attacks they can handle. They will decide how should they reach a decision. So basically, these ended up being the fundamental constructs in the protocol. Of course, we're not saying that these will be the only sort of four atoms. For the start, we believe these are the four fundamental atoms, and we believe in the future more atoms can be maybe added if there's possible that some protocols might require some different atoms which are indivisible and they need to be the founding ones. So yes, they can be added. But according to us, these are the four basic which will be part of almost any protocol.
Nice. That really makes sense. So now that we've got our atoms, we need in chemistry we need compounds, right, as well. So there's six of these in the paper. Can we maybe run through those? What are they and why?
Yes. Now, once we got the atoms, now we need to do next, as I just said, we need to make some sort of an element, combine these atoms. What can we do? And in some sense, what we view elements in this paper are basically phases of the protocol. So we have different agreement protocols. We could have 2PC, 3PC, which are commit protocol. We could have Paxos style protocol, which can handle crash failures. And then we can have PBFT style protocol, which can handle all the malicious attacks. So in all of these protocols, what is something which are common? And that is what we try to term as the elements, basically the common phases. For example, a very common phase in any protocol will be proposal. Someone has to, because if a protocol is being run, that means someone must have sent a proposal. There must be a leader, there must be some party who has actually said, hey, let's run this proposal, let's complete this transaction, let's execute this transaction. And that is what we call as the one of the key elements. And often this proposal is sent by the leader to all the other parties, or in protocols like distributed protocol, maybe they could multiple leaders, all of them could be sending proposal at the same point of time. Then once a leader has actually sent a proposal, other parties need to take some decision. Generally, the idea is that these parties try to reach an agreement what to do with the proposal. So they try to vote on the proposal, and that is according to us the next element, where the parties will decide to vote whether they want to actually agree to what the primary is saying or the leader is saying, or they do not agree. In some protocols, the vote might actually even determine they want to even abort the transaction or commit the transaction. So the idea of the next element is to vote. Then once the voting is done, now a common decision has to be reached. So the votes, all of these parties, they vote, they send these vote to the primary if it's a primary backed protocol. And now what the primary will do, it will collect all of these votes. And once the primary has actually collected all of these votes, it needs to gauge what is the result of this voting. Has everyone agreed or has everyone disagreed? So now based on those results, now the protocol needs to move forward. So if it is possible, some protocols say that just enough votes are, once we get sufficient number of votes, we can simply prepare or we can simply commit. And that is what our next elements are. Based on the common decisions, protocols try to decide on the global decision. Based on this global decision, either you can just prepare, move the protocol to the next stage, or if you want multiple steps, you can also commit. And similarly, we also have here another element which we call as decentralization, because if the protocol is just being led by the primary, then your prepare and commit are happening led by the primary, because everyone is sending to the primary, then primary is sending response back. While you can have a decentralized version where you say everyone can communicate with each other. So again, we have decentralized version of this protocol. And in the paper, if you'll have a look, we try to show us a symbol to represent this decentralization. So we are trying to show the difference between centralized prepare and commit and decentralized prepare and commit, basically saying who is leading to these next decision-making steps. Finally, when all the decision is done, you need to actually execute the transactions. Execution means you need to actually find what the result is, and then you need to reply to the client. So that stage, we are again represented through an element. And often when you have a lot of transactions and you have reached completed execution and you have passed through a lot of history, you need to do some checkpointing and garbage collection. So we again make us element for that. And finally, it is possible that if the protocol is led by some leader, then that leader might fail. And if the leader fails, then what should you do next? You need to select a next leader. And once you select a next leader, you need to ensure that all the other parties know this is the next leader and they all have the common state. So we believe leader election could be another element. So if you see in premise, all of these elements are trying to show that different phases in protocols are sort of like common in every protocol, and these are exactly the elements. That's what we're trying to show.
Nice. So yeah, just to summarize, the 6 different elements we have here. So we have proposal, vote, prepare, commit, with obviously the decentralized variant as well, execution, checkpoint, and leader election. Great. Yes. We've got our elements now. Now let's like cook up some protocols of these elements, right? Let's mix them together. So there's this really nice bit in your paper where now we've got our framework. You analyzed like 4 of probably the most famous agreement protocols out there. So maybe we can run through each one and just talk about how this framework can be used to describe these algorithms.
Yes, I think that's a great thing. So now what we'll try to do is that we'll try to take the 4 atoms and the 6 elements, and we'll try to design 4 of the protocols. Basically, we'll try to see how can we design 2-phase commit, 3-phase commit, Paxos, and the PBFT. And the reason we chose these 4 basic protocols is because 2 of them come from the commit world, one of them comes from the Paxos, a crash fault tolerant world, another one comes from the malicious fault tolerant protocols. So to understand that, what we'll try to do, we'll start with 2PC protocol. And to see 2PC protocol, we know that in the 2PC protocol, the assumption here is that there will be multiple parties, and these parties, what they try to do is they try to reach an agreement where a transaction could be committed or has to be aborted. And the whole point here is that generally 2PC runs in a partition system where the idea is that all the parties are managing their own data. And then that is why they need to take their own individual decision whether they can actually order the transaction or not. So in some sense, all of these parties are sending a vote of aborting or committing the transaction. So the first phase would be for would be also our first element, which is proposal. So whichever party has access to the transaction, it says, let's propose. And then now it sends this proposal to all other parties. And now all other parties, when they get this proposal from the leader, what they do, they decide to vote whether they should commit or abort the transaction. And the thing here is that all of these parties are individually making a decision. They are trying to look in their own history and seeing whether they can individually abort or commit the transaction or not. And this is why we represent this type of voting sort of differently from the voting we do in Paxos and pivot, which I'll discuss next. And once the primary gets the decision from all the parties, it decides, okay, if everyone is agreed to commit the transaction, let's commit. If one of the person says, or more, several people say that let's abort the transaction, they'll abort. So the idea is to show that there's a next phase, which is the commit phase, whether you make a common decision what you need to do with the transaction. And based on this discussion, now the transactions are executed. If you need to actually execute the transaction or not, you need to reply to the client, you need to add update in the history, write in the log. So that's what being is done, execution step. So that is a very simple two-phase commit protocol. But now once we've done the two-phase commit protocol, let's try to see what do we need to do in the three-phase commit protocol. And this is where things become interesting. The extension between two-phase commit protocol to three-phase commit protocol is quite trivial if we try to see it from our framework's perspective. Basically, the problem with two-phase commit protocol was that it could be blocked. So prior work showed that if the primary fails and one of the replica fails at the same point in time, then it is very easy to create a scenario where all of the replicas are stuck, they are not able to make any progress, and system comes to halt. So to avoid that, three-phase commit protocol came, and the idea of three-phase commit protocol was to say that, hey, before you actually make any decision, ensure everyone is ready to move forward. So that's why three-phase commit protocol had a prepare phase, and this is where another element comes. So when we said you can either commit the transaction or you can first prepare and commit the transaction, and that is where three-phase commit protocol comes. So the proposal is same. Leader sends the proposal, everyone is voting. After everyone votes, now the leader does not make the global decision, final global decision. What all decides whether it can actually move everyone to prepare or it can ask someone to come. And that's what is happening. And once it knows that everyone's ready to move to commit, it again finally does the committing the transaction. So basically we have added two more phases in the whole, two more elements in the whole framework. So if you see in the two-phase commit, we had four elements: proposal, vote, commit, execute. Now we have six elements: proposal, vote, now you prepare, then you again vote, then you commit, and then you finally execute. So that's what three-phase commit protocol looks like. Okay, so now we did two-phase commit and three-phase commit protocols. So how can we build Paxos from this knowledge? And that is what we were trying to think. And so what does Paxos do compared to two-phase and three-phase commit protocol? Well, if we see in two-phase and three-phase world, the idea what was happening is that all these parties were making their individual decision. And in Paxos, what is happening, there's a notion of a replicated systems. So all the parties are working on exactly the same data. They have same sort of data items. Whatever the transaction comes, they're trying to order it exactly the same way. And to do that, we need to run through a consensus, which is Paxos consensus. And what we'll try to see here is that the phases being used are exactly same as 2PC. For example, in the Paxos, let's do a leader. There's already a selected leader, and that leader has to propose. So the leader proposes a transaction. And now the same thing was happening in 2PC. The leader was proposing. And now everyone is voting. But what they're voting here is that they're trying to see whether they can actually agree with the primary or not. So they simply send their agreement to the primary. If the primary receives agreement from majority of people, in this case, it will be F+1. As we said, the quorum size is different. In 2PC, the leader had to listen to everyone. While in Paxos, the benefit is leader only needs to listen to F+1 people. So once the leader listens from F+1 people, it knows that, okay, F+1 people have agreed to follow the decision. So he goes ahead and commits the transaction. And then finally, the leader asks everyone to execute the transaction. So exactly same four elements, which are being used in 2PC, are being used in Paxos. But the only distinction is the way they are being used. And in 2PC, the voting is done. Everyone does a distinct sort of voting. They have their own states. They might be working on partition data. While in Paxos, everyone is working on exactly the same data. While in 2PC, the leader needs response from everyone. While in Paxos, only F+1. And similarly, this allowed us to create PBFT now, because seeing we already made Paxos, what do we need to do in PBFT? In PBFT, the difference here is that you can have malicious attacks. So because you can have malicious attacks, like in 3PC, you had to wait before you reach your decision. In 3PC, we had to first prepare and then commit. Exactly same thing what we are doing in PBFT. We first have to prepare the replicas and then we commit the transaction. But the key difference between 3PC and PBFT is same what is between 2PC and Paxos. And of course, in PBFT, the quorum size is increased. The quorum size, which was F+1 in Paxos, is now 2F+1 in PBFT. So the phases are exactly the same. So this is how we were able to define the 4 different protocols using just these 6 elements.
Hearing you say that then puts it all into perspective so much more in a clearer way in my mind than me reading these textbooks over the years. It just seems it's a really nice framework and it fits it all together really nice. I mean, the thing that was kind of, I guess, not obvious to me initially was like the way that basically you kind of, what's the word is, I was initially thinking that the elements could only be used like once, right? You could only use the prepare once, right? But you can use them multiple times, right? That's, I guess, the secret sort of source to it in a way, I guess. Is that you can mix and match the order in which you have these elements, right?
Yes.
Which is awesome. So I guess building off that, and you hinted to it earlier on as well, is that this framework will allow you to maybe create or open to sort of the space up to thinking about different sort of combinations of these elements that haven't maybe been explored yet. And I know you have a section in your paper where you look at more complex protocols. Maybe we can touch on that, and then you can maybe say about the potential space you think's out there for kind of what this framework opens up.
Yes. So you're absolutely right. I think that was one of the things, also a driving goal for us. We wanted to just not restrict ourselves to these 4 protocols. The idea was to say that this one framework could actually aggregate all different protocols. And in fact, while I was explaining different atoms and elements, I also said that they could be a centralized and decentralized version. So I think we also show in the papers, like the Paxos, which I was just describing, was the leader base, where the leader was actually driving the Paxos. Leader was sending the proposal, it was collecting all the responses and taking a decision. We also show in the paper, we can simply make a decentralized version where once the leader has sent the proposal, now the leader is no longer in the middle. All the replicas can go ahead and talk with themselves. They can come on the common decision and they can finally execute. Similarly, we can have a decentralized version of PBFT where we can say that all the replicas can communicate with each other and they can reach prepare and they can then finally commit. In the paper, then we go again with several other protocols. I think I'll not discuss all the protocols, but to give a quick glimpse, we talk of protocols where there can be notion of speculative consensus. For example, some protocols say you don't need to wait for decision to be committed. Basically, you can take an eager decision. And that is, for example, they're having protocol like ZZY in BFT world. What the idea of this protocol is to say that, hey, as soon as the primary sends me a request, a replica will go ahead and execute the request. And then in the future, they will decide whether that request can actually be committed or not. And in case it could not be committed, then they need to roll back this state. So we were able to simply express this in our framework because why? We just needed 2 elements. We needed prepare proposal phase, and then we need an execution phase. Of course, if we need to show the failure, then we have to design a different model. And similarly, we were able to show several other protocols. For example, all of these protocols we were talking about assumed right now that there's only one leader and that one leader is sending the proposal. But what if there could be multiple leaders? I mean, there are several protocols, like there's a Meneses protocol, there's an RCC protocol. These protocol, what they try to say, you can have all the replicas maybe at the same point and they can act as the leader. That means that in such a protocol, several requests are getting committed, prepared at the same point of time. So in our framework, what we try to do is that how can we actually leverage this? And if we're going to show that multiple consensus are happening at the same point in time, how can we represent that? And for representing that, it was very simple for us. What we added was just sort of like a subscript showing that, hey, we sort of like said that these phases, we found what are the some sort of phases which everyone will be doing. We subscripted by I means how many constants do you want to run in parallel. And then we said that we added a new element where we said that if all of these constants are happening in parallel, then you need to aggregate the response, because we, these replicas are running multiple constants. They're running constants because they have multiple leaders. But ultimately, they need to execute these requests, and they have to come with a common order for all of these consensus. So we need a phase where this common ordering can be generated. So that is how we express parallel protocols and multi-primary protocols. And similarly, we went to other style of protocols. We said that how about protocols or systems where there's both sharding and replication? Like Spanner is one example of such system. So we try to express those systems where we show that if you want to do sharding, uh, how do you represent that? And then you can even do replication. So we just assess what we saw, that it was just some sort of change of notation. We needed few more notations, but the phases and elements still remained the same. The only thing was that, yes, if you have multiple shards, you might require these shards to communicate with each other. And for that, we added a new element where we said that maybe you need an inter-shard communication. And that inter-shard communication is a new element for us. And this element was interesting because this also helped us to define a different style of protocol, which is basically say the geo-replication protocol, where you have multiple clusters and each cluster is running its own consensus. They're still working on the same data and everyone is still replicating the same data, but they now need to communicate. So that is what we are trying to do.
Next question is, so far we've been talking about the happy path, right? So we haven't really touched on failures too much. How did you go about incorporating failures into your framework?
I think you asked a very good question. I think this is a concern for almost every protocol. I think, and that is what is challenging for every protocol, is how can we actually handle failures, and can we actually design a common path for all the failures? Can we actually see that even failures have same sort of elements and atoms like the happy path as I was talking about? And actually that is quite true. So because if we see a very basic failure model, the very basic for failure model talks to us that there has to be some leader who has failed. And if the lead, because if a non-leader has failed, then basically that non-leader just needs to get up and it needs to be recovered by itself. It can ask others for help. But if the leader fails, then the system has an issue, because now the leader has failed. You need to select new leader and you need to ensure that all the replicas are again on the common state. And that is what we're trying to do. With the leader election, we believe there's a possibility of creating a common set of elements here. And that's why we'll design 4 different elements. The first element was timeout element, where we said that how do you know that the leader has failed? So the idea is that every replica is actually waiting for some action to happen. And if that action does not happen for a prolonged period, then that replica will sort of time out and they need to take the next step. In our case, what we'll say is that the replicas are waiting for leader to do something. And if the leader does not do a specific task, then they have to time out. And once they time out, they now need to do next. And the next thing generally is that they announce, because if I'm a replica and I've timed out, I need to know that how can I make progress, and I cannot make the progress by myself. So generally I need to announce to everyone and say, hey, I've timed out, have you also timed out? And based on that decision, we can do the next step. And often the idea is, if every replica is announcing with each other, now they will come to a common goal that they'll find out the leader has actually failed. So now they need to select a new leader. So the whole process of leader election, and leader election is a very famous problem. I think there has been a lot of papers and distributed systems and databases about how to do leader election. So this simply fits in here. So after you have done timeout, there's announcement, the leader election comes. And once the leader election has happened, the idea is that everyone should reach a common state. So generally the idea is the leader will ensure everyone has the common state, or in like Paxos style protocol, the leader might check everyone's log and maybe try to set their logs into correct state. Or in BFT style protocol, the idea is the leader will ensure it gives everyone the common state they can all reach, and so that they can again start the consensus. So this is exactly what we believe are the 4 elements, and these 4 elements can help to define any failure model. And in the paper, we actually show how can these be used to represent PBFT's failure model, because we believe if you're able to represent PBFT's failure model, we can also represent Paxos failure model, which is somewhat easier.
Awesome. Yeah, I'd recommend the listener going and digging into that and looking into that some more for sure. So given the framework here, how did you then go about evaluating how effective the framework is and how useful it was? Like, and how did you experimentally explore this? And I guess kind of what questions were you trying to answer?
Yes. So I think that is a good thing. So I think so the key challenge for us while experimenting was to understand how these different protocols are faring with each other. First of all, at least in this paper, we are not presenting a new protocol. So people already know how different protocols are supposed to behave in each other. But one of the key goals of our implementation and evaluation was try to give a highlight that now that we have a framework which can actually express different protocols and even their failure model, can we similarly have an experimental framework like that, where we can actually um, pick and play different protocols? We can have like these elements I'm talking about, like this proposal, vote, prepare, commit, and all. Can we have all of these elements as sort of like modules? And if we have these elements as modules, and then these atoms are basically the general characteristics of different protocols, then we can simply plug and play these modules and we can create different protocols. And that is exactly what we try to do in the experimental framework here. In this paper, we specifically use Bedrock as the framework. And why we use Bedrock? Because in the prior work, we have used Bedrock to actually test different types of BFT protocols. So in this framework, what we did is that we actually leveraged the Bedrock to create even 2PC, 3PC, and Paxos. And what we were trying to show here is that just by having these modules, so we were easily able to not only create these protocols, but even able to achieve the same performance what is expected. So in general, what we expect is that you expect 2PC to, assuming there are no failures. So assuming there are no failures, the assumption is 2PC will perform good because it just have few number of phases, all the replicas will achieve high throughput. And similarly, the assumption here with the PBFT would be the most expensive protocol because it has 3 phases, all-to-all communication, and the leader has to send message to all the replicas. And there's somewhere in between there will be 3PC, there will be Paxos, and that is exactly what we are able to yield the same results. And we don't. The whole aim is that now that we have created such a framework with these small elements, and that framework is able to express these 4 different protocols. We also evaluate POE, which basically reduces one phase from PBFT, and we try to show that POE is actually performing better than PBFT in the experimental. So the idea is that with these 4-5 protocols, which we are now able to create, maybe in the future we can also add more elements, or maybe we can use these existing elements to create newer protocols. So this experimental evaluation is sort of like an initial step to allow developers to create a framework where they can easily mix and match different protocols and create newer designs.
Awesome. Yeah, I have a few questions that kind of fall out from that. The first is Bedrock. I mean, can you tell us a little bit more about that? Because I'm not familiar with that system at all.
Yes. So the Bedrock is actually work with one of the co-authors. So one of the co-authors on this paper is Mohammad Javed Amiri. It was from UPenn. So it is his ongoing work. And the idea of the Bedrock is basically trying to understand how different BFT protocols work in practice. So I think Mohammad has done a good job there. He tried to basically implement almost 10 to 15 style different BFT protocols. And what it tries to show is that how in practice these protocols are performing, what is their throughput, what is their latency. It could be in the single cluster, it could be across geo cluster, multiple regions and continents. So I think that is what he's trying to experiment in Bedrock. And I think that is why we use Bedrock for this framework.
Sure, yeah, that makes total sense. I mean, I really liked what you were saying as well about this having like these plug and play modules for each element, right? I mean, I can imagine me just coming along and writing some config files. Today, I want to try out this new protocol I think could be great. I want to evaluate the properties of it, throughput and latency, see how it performs. And I can just like plug and play all these. I want to do this round, I want this element, that element, and just kind of stitch them all together. That's really cool. So how easy was that to implement? And like to have these sort of independent modules, is that quite difficult? Or did you find things leaking into each other?
Actually, that's a good question. So in this paper, interestingly, we use Bedrock. So this was something sort of an attempt which we also did at Resilient DB while we were doing this thing. So in both of these systems, I think the idea what we did was we first started by creating a simple protocol. Let's say we just took PBFT, for example. And once we designed PBFT, we saw there are very common phases, like the same thing which we're talking of elements here, right? Like the prepare and commit, the same things have to be done in there. And these could be simply created as independent modules. Of course, as you said, that they will have some common parameters and these parameters will be accessing each other. So that is the same thing which is going to happen even here. But we could easily separate out these as functions, like a function called as prepare function, as a commit function or a vote function. And now for these four protocols, for example, we realized that these functions could be similarly used. But yes, of course, there were some nitty-gritty details. For example, in 2PC, we realized that the vote is basically telling whether you want to actually commit or abort the transaction, while in PBF2 Paxos, vote basically means I'm ready to agree with the primary. So in that case, we had to have some changes. We have to say a vote for commit protocols while a vote for any other specific startup protocol. Similarly, execution in sense, I think it was quite easier for almost all the protocols, were because you're just simply executing the transaction, or even the leader election was quite simple because you're. So some of these phases were very easy to separate out, yes, but there were some other phases which have which use common global parameters, and I think that is for there you have to link to each other. So there I think the developers have to do some edit.
Okay, how big was the implementation of it for this? How long did it take?
um, okay, so the two things, as I said, because part of the thing was we already had Bedrock with us, so we didn't have to do a lot of implementation. The only implementation we had to do was for 2PC, 3PC, and Paxos. But I think it did not take much time. It just took us matter of, I believe Mohammed told me it just took him like couple of days just to implement these few protocols, because and I think that was the beauty about it, because generally if you're going to write a protocol, it is going to take you a lot of time, but if you have a plug and play system, it just takes a couple of days to create multiple protocols and simply
Well,
test.
I was thinking the answer is going to be in the magnitude of months rather than days. Wow, that's awesome. Cool. Yeah, I guess kind of spoke about all like the like how effective the framework, how useful the framework can be, and you spoke about the evaluation. But are there any limitations to the framework? Like, what are the areas where it doesn't maybe fit perfectly?
Actually, that's a great question. In fact, you yourself, while asking me the question, pointed out a limitation. Interesting, and there is sort of a limitation. I think the limitation in the framework is sort of like the system right now itself is not fully expressive. We need to do much more. I think to start with, one of the points which you said was there are protocols which talk about read and write sets, where you need to specify read and write sets earlier in time, and like the deterministic protocols which say that you need to know the read and write sets of the transaction ahead of time. And I think at this point in time, our framework does not provide a way to express such protocols, but we need to think about how can we do that. And similarly, right now, all the protocols that we have discussed, we make an assumption that they have sort of a partial synchrony or synchrony assumption. The idea is that like the real election, with the assumption here is that we're assuming the replicas will time out, and when they time out, they will announce, and then they will go and select a leader and they will do forward. But what if the protocol is asynchronous? And there are sort of many asynchronous protocols where there's no notion of timeouts. So how do we express such protocol in the framework? I think we still need to do on that. And similarly, our protocol right now, for example, does not talk about things like reconfiguration. I mean, what if a node wants to join the system? What if a replica wants to leave the system? Can we express those type of things in our framework? That is something, again, we have to think about a challenge. So and some more protocol, like there are protocol which have a DAG. Like right now we are assuming a single ordering, and interesting, most of these protocols assume there's a single, but there have been recent protocol which assume DAG based ordering. There's a partial ordering happening. So again, we need to think, how can we include these type of designs in our frame?
The DAG thing is interesting because I don't know whether this is related to what I'm going to ask. Is that how would you capture different consistency guarantees in the protocol in this framework, and is that something that you're thinking about exploring as well?
Actually, I'll say that that is actually one of the things which we are thinking about exploring. I do not have a right answer right now. That is something which also hovered around, like, because right now we are assuming just one guarantee. We're assuming a single ordering across all the replicas. But I think, yes, you're right. We might have to think about eventual consistency, or we might have to causal consistency. Can we actually even talk about these things in that framework? Might be quite interesting. We don't have a right answer right now, but this is something we are actively exploring right now.
Fantastic, yeah. Plenty of interesting things to be going at. Cool. Yeah, I guess my next question is then, has maybe as a software developer or someone working in databases or data management, how can I leverage the findings from your research and the things you find, and what impact do you think they can have on someone's day-to-day working life?
Yes, I think so. For that, I think I'll go back to like a few years back, and I'll try to say, like, why did we actually even come up with this idea? So I mean, this was not something which we have been thinking for years, but I think something. During my PhD, I think we have been working on like these different consent protocols, and that is where we designed this framework which we call as resilient DB. So idea is basically which expresses different BFT protocols, and it's similar to Bedrock. And the idea of our resilient DB framework was basically trying to say that how can we express different protocols. The idea was not exactly plug and play, but just to give a framework which can allow implementing different protocols. And we found this challenging because there were speculative protocols, there were geoscale protocols, there were sharded replication protocols. We were trying to have these challenges, and I think this is the same sort of challenge which even developers had, because I think one of the person I was working on this framework, he's now working at Oracle and or other places, and he also said that he met different developers and these developers still find it hard to design Paxos, because it's very unclear to people, like, how can you even do simple sort of like replication or safe replication. And I think the use of this framework would be like, a lot of people easily know about two-phase commit, three-phase commit protocol, because these are the basic database protocols which are taught to anyone. And if we can show that other protocols are quite similar to these, like protocol like Paxos or PBFT are quite similar to this two-phase, three-phase protocol, then people can easily reason about them. And this reasoning can actually help in expressing different protocols. And I think might easily help developers to develop these protocols and create the fallback case, because often I've seen developers saying that, hey, PBFT is hard. Why it is hard? Because, oh, the failure case is very hard. You have to think about a lot of sending a lot of messages or receiving or actually generating the common state. We believe that may not exactly be the case. It might just be a simple way of expressing.
Fascinating. Yeah, I think it definitely gives like a common language for people to talk about these things, because I think we all kind of have in our heads otherwise our own way of understanding these protocols, right? And then often my worldview is not compatible with somebody else's, then we kind of get confused on terminology and whatnot. So yeah, definitely kind of giving people a common baseline to talk about these things on is a massive win. And I think as well, I mean, you touched on it a little bit there where you said that, I mean, I always get this as well, like two-phase commit, three-phase commit. Yeah, these are pretty, like, okay, I can understand these. You go into Paxos, and Paxos sort of has this like myth associated with it of it being difficult to understand, right? And it kind of it feels impenetrable almost sometimes. But when you break it down like this, you just say, oh no, it's not. We're just doing a few extra phases, right? Like, and that kind of almost demystifies it and sort of takes away sort of the scariness of it almost. So yeah, definitely. Yeah, I agree with it. Agree with everything you're saying. Cool. Yeah, I guess when you were working on this, then what was maybe the thing that you kind of learned across working, like that kind of caught you off guard, maybe, and you were like, huh, that's interesting. I didn't expect to learn that sort of thing.
Yes, I think two things were quite interesting to me, especially while I was trying to understand this framework. Was specifically we saw, as I was describing the protocols, we saw there is same sort of similarities between PBFT, Paxos, 2PC, and 3PC. I think that was quite interesting. And specifically similarities, not just similarity in the saying that, of course, they're agreement protocols and they have similar style of phases. What it was like, the number of phases were exactly the same. And like the only difference what we found was whether they were actually replicating the transactions or they were not replicating the transactions, whether they were actually nodes were taking their own decisions. And that was quite intriguing to us because we were like, okay, they're not quite different protocols. They have same style of phases. And I think this is what exactly I think what the challenge has been in the community. And we all have been looking the protocol in a different way, but they're exactly simple extension. You just add more phases to pack, so it becomes PBFT. You added more phases, you increase the quorum size, now it's PBFT. You just change the model from like you change the quorum size, you decided who will be making the decision, now it's actually 2PC. So this is what was quite. And now how should I parallelize the protocol? You just allow replicas to run multiple constants at the same point in time. Now it's a parallel protocol and just need to collect and aggregate the state. So I think this was quite interesting to us, that, and this was something I think we didn't realize it is quite easy to understand. Even after working for several years on these protocols itself, we ourselves did not realize it until we actually started making down this framework and realized, yeah, it is quite, we are using exactly the same states, and that is exactly easy to define.
Nice, yeah, for sure. I mean, when you were working on it as well, I mean, when did the idea sort of happen for initially? When did you decide, you know what, we're going to do this framework? How long back was that?
So I think in some sense, the idea for this, the idea for this specific paper, I'll say, was just last year. But the idea in general to design such a framework or way to express had been there with us for, I think, since 2018, 2019, I'll say that. Since 2018, 2019, we wanted a way to express. And I think the reason why we wanted to express is because as like everyone, when I started with just understanding 2PC, 3PC. And then, of course, Paxos has been difficult for everyone, I think. And then I just switched to PBFT, and then I was trying to understand. Once I understood PBFT, I think I went back to Paxos and like, oh, it's not exactly difficult. It's quite similar to what PBFT is doing. It just reduced phases and you don't require that much communication in some sense. So I think that is what was quite interesting for me. But at that point, even I've still started, if this is the case, why don't we just simply express all these protocols in one framework? And actually that helped us to design few other protocols. So I think subsequently, while I was understanding these protocols, we had this GOBFT paper, which was at VLDB. And we had another paper, RCC, which was ICD. So all of these papers, and I talk about these protocols actually in the paper, also in this chemistry behind agreement paper also. So the protocol POE, RCC, and GOBFT, all three of the protocols, they came to us in a matter of like 1.5 to 2 months. And why they came to us? Because once we saw that how similar the phases were, we were easily able to split them. We saw that, oh, now you can simply parallelize and that will give you performance. And now you can actually replicate the concerns across clusters, and that will give you another different design, and which will help to scale more. So I think since then we were trying to think, okay, maybe we should come up with a common framework, and finally I think it happened.
Fantastic. You thought, yeah, finally, we're gonna have to do it. We're gonna have to write this framework down now. Awesome. Were there any like dead ends you hit though when you were trying to when you finally came to the point of deciding, right, let's write this down? Were there some kind of things where you hit a bump in the road sort of thing with it?
Yes, there were a lot of bump in the roads. For example, when we started with the 4 simple protocols, and I think they were very easy to express. But I think as we move forward with further protocols, we realized that we had to come up with different notations, because I think if, like, for example, in chemistry, right, if you're trying to create a chemical bond or something, we have different type of arrows, or do you have different type of bonding? Like for benzene, you have like a hexagon structure, or you have different structures. Like similarly, we were quite perplexed. How should we express multi-primary protocols, or how should we express sharding and replication? Or, in fact, if we are going to express sharding and replication separately, it's fine, but how should we express them in the same diagram? So for a single protocol, and that too in a concise manner, we cannot just have like some comments written on top of protocol, because that will not be quite interesting. And I think for that we had to iterate over many times, because we first, I think we remember we were trying to make some sort of like some sort of brackets, or we were trying to make some sort of figures or square boxes, and they're like, no, that's not concise, that's not clean enough. I think that was quite interesting, challenging for us to design how to come up with this compact notation. And in fact, we still believe like if future protocols, as some of the things I was expressing, telling that we yet have to discuss in our framework is like about different deterministic protocols, maybe we still need to come up with new notations and expand the set of elements, atoms, and these notations to include this protocol. So I think that was quite challenging for us, and yeah, and that will still be challenging, I believe.
Yeah, I think that's a nice segue into my next question. Is like, what's next on the research agenda then? Where do you go from here?
So I think all the open problems, I think we have started looking at them. I think right now, for example, we only looked at a very small protocol. I think in this paper we only looked at like around 20 plus protocols, something like 20, 25 protocols. I think we want to move beyond that, because in just, for example, in BFT world, for example, there are like 50 plus protocols, and there are chaining protocols. There are protocols which assume the lead election is happening just part of the happy case every time it's happening. And then there, as I talked about, deterministic protocols are there. And even in Paxos world, there are sort of different type protocol. I think right now what we're trying to look next is we're trying to see how we can express more of these protocols. How do we have to define the notations? Maybe we need to come up with a much more precise set, because I think right now this is just a start, we believe. And I think the largest we want to expand from this 25 protocols to like 50 to 100 protocols we can have. And then we can have, say, hey, now this is the whole suite of protocols, and this one language can actually express. And maybe beyond that, we are also trying to think, maybe we can have sort of like automatic proof generation for this protocol. Like, for example, we're trying to think, can we actually use things like data log to actually write down these protocols and prove that whatever our designs are, or these elements, we can simply plug and play there, and we can show that we can easily design new protocols. So I think those are some of the goals which we are trying to actively think about right now.
Awesome. Yeah, I'm really looking forward to seeing where this goes. It'd be nice as well to like. I mean, you mentioned it earlier on about talking about resilient DB. Maybe it'd be a good time to talk about some of your other research as well that you've done. I mean, you mentioned like a few VLDB papers, an ICD paper. Yeah, tell us what else you've been up to in the recent times.
Yes. Yeah, I think so. Resilient DB was something which I started during my PhD. I think, and that is a system which we sort of created. And I think that also relates to sort of the key focus of my research. So my research mainly focused about designing fault-tolerant protocols which can actually handle malicious attacks. And I think with Resilient DB, we wanted to do that. We wanted to basically create a framework which has the same client-server model, but now you can actually introduce different protocols like which can handle malicious failures. And we had several of our protocols there. We have RCC, we have PoE, we have GeoBFT, we have Ring BFT. So these are different protocols. So idea of these protocols in different environments. Some work in geoscan environments, some work in sharded replicate environments, some assume multi-primary, some simply reduces phases. So that is what we are doing. But right now, so that was something which I did as part of my PhD. But right now I'm doing something more, in the sense now we are trying to look ahead of just consensus. We are trying to look as what is beyond consensus. We are trying to look at, for example, serverless edge framework, and we are trying to see if we have a lot of these serverless functions and we have these edge devices, how can these edge devices make use of these serverless functions, but they don't have to actually interact with this edge a serverless function, in the sense they don't want to store anything on the serverless hardware or cloud, and how can they do that in an efficient manner? And assuming some of the edge devices might be malicious, maybe the cloud provider might just fail in some case, such a scenario, how can we actually provide efficient response? That is something which is upcoming in our ICD 2023 paper. Then we are also working on something about trusted hardware, where the assumption here is that you have such systems which have trusted hardware, and we saw that a lot of these systems use protocols which claim to have more benefits than they actually have. And this is something, one of our work which is under process. And the idea here is that to show, we define a new suite of protocols, and which we call as flexi trust protocols. And the idea is that these suite of protocols are more efficient than the protocol which use trusted hardware, or the protocols which do not use trusted hardware, both of the categories. And our idea is that our protocols are more efficient. They provide higher throughput, lower latency. They provide um, they're more resilient to liveness attacks. And this is some work which we are doing in parallel. And finally, I think one more silo research which we are trying to look for is like assuming you have multiple clusters, and these clusters running whatever protocol they want, and how can these clusters talk with each other. And why is this more interesting? Because these clusters could be anything. The clusters could be just organization, like for example, your top organizations, they want to communicate with each other. Now if they want to talk with each other, then they need some sort of a trusted person to relay their messages, or some sort of a media which is exactly specific for their uh, communication. Someone needs to handle and manage that. But if I don't want to have some trusted network, I want to do this thing distributed manner. I don't want to trust anyone. So how can we do that? And that is what we are trying to look at. Of course, there's a simple way. You can ask everyone in one system to talk to everyone in another system, but then you're creating too many copies of the message. So we are trying to see if we can do this type of communication, but in an efficient, copyless manner. So these are some of the directions which I'm trying to explore right now.
Fascinating. It's like this is a whole host of really interesting like directions there. How do you decide which to pursue, and how do you even come up with these in the first place? What's your process for doing this?
I think that's a very interesting question. In sense, like I cannot just give credit to myself for coming up with most of this. I think we have a lot of like brainstorming session where I think a lot of us are just sitting around and trying to think over the ideas. I think one of the things which we always do about, and I think pretty sure everyone does, is like we try to see what might be relevant to industry or to wider audience. For example, like in the protocol which I was talking about, the communication protocol, the idea was basically trying to see is that it's we believe it's a common problem for multiple organizations to talk with each other, and there have been some solutions in that direction. So we were trying to see what can we do in that space. We didn't want to do something with trusted parties. We wanted to do without trust, and we wanted to also reduce the commission cost. So that is where it comes from. And then similarly, we were trying to think, oh, there are a lot of hardware these days which have some sort of components like SGX is there, Intel's SGX is there, or the ARMS enclaves are there. Amazon also has its own small sort of trusted computing is there. So these type of machines are coming forward and people are trying to use them for computation. Can we design concerns around these type of machines? Of course, people have done in the prior, but we first tried to find some limitations. We found that there are actually limitations in these designs, and then we tried to come up with efficient design. So I think most of the times when we try to look at problems, we're trying to see if that problem actually relevant, can actually be implemented somewhere, can someone actually use it, and of course you have to read what other people have done. So I think that is which gives an idea about what is something more interesting which we can pursue, I believe.
I guess if you put your prediction hat on now, or where do you think things are going to look like in like sort of 10 years time? Like, what do you think are the biggest challenges we're going to be facing now that we need to solve for the next sort of 10 years, basically?
That's a hard question in the sense.
It's an impossible question. I'm sorry.
Yes, yes. I will not deny that. Okay. First of all, there's a lot of research in AI, and people are doing excellent and beautiful work in that direction. I'm not even an expert to even comment that, but I believe AI in databases is very interesting. A lot of people are doing. But I'll just talk about from the perspective of a person who's looking at distributed systems and databases. From my perspective, I believe I think through achieving that extra throughput and low latency would still be an interesting problem. But I think a lot of focus has recently moved towards designing energy efficient systems. And in fact, one of our works, which is also under submissions, we are actually trying to design. So, for example, because I work in a malicious attack space, there's a whole world which works on protocols which can handle like blockchain protocols basically, and we have been looking at those direction. But I think traditional protocols like search consume a lot of energy, so I think we have moved towards designing some protocol which can consume less energy. In fact, the product in this trusted space work which I was talking about, there also one of the graphs which we are trying to show is that our designs try to use less energy, and I think energy would be quite key. I think because a recent presentation I were attending from Google engineers and researchers, they also were claiming that the companies are driving towards having designs which are consuming less energy and are more efficient. I think that is something which might be interesting. Another direction I believe it might be more interesting is security and privacy. I think interestingly, some of our works coincide in that direction. Right now, most of the database works, they don't cater to security in general. They actually works are moving towards privacy. We've seen a lot of privacy, how to secure the data of your client, how to ensure the data is not leaked. That is something very interesting. But I think still we are not looking at malicious attacks per se. There have been a lot of works in systems community, but I think database community still has very few works. But I think this will become more relevant because attacks on databases are quite common. Data breaches are happening very much. And I think very recently we just saw like the there was a FAA thing where the flight control got completely shut down in the system because of poor replication in some sense. So I think such type of attacks could have been caused by even hackers where they easily compromise the data. So I think security might be quite interesting. So that's where these BFT protocols will come into use. Right now, nobody uses them, saying that they're expensive, but I believe they will be much more in application in the future.
Awesome. Yeah, I guess maybe as well as they become, if like efficiency becomes more important, energy efficiency, like those protocols improve and then they become more usable, right? I guess, or more appealing to use because I mean, right, economics, right?
Yes.
I guess it's time for the last word now. So I guess what's the one takeaway you want the listeners to take away from this work in this paper?
So I think one simple takeaway I'll say is that consensus protocols or agreement protocols are not hard. What is hard is the way they have been expressed, and there's a huge disparity in their design. And this paper tries to amend those disparities. It tries to promote a single framework which can help express these protocols. And our hope is that this one framework can help in designing future protocols. Newer protocols can be expressed in this framework. And maybe we can simply keep on extending this framework to express other protocols in sense. So this framework can act as like a bridge between different communities which are using commit protocols or crash fault tolerant or malicious fault tolerant protocols. I think this framework can become a bridge, and this theorem provers which are used by one community can be used in another community to express the same protocols. Maybe the designs can become common, practices can become common by using this framework. That is what I believe is useful for this framework.
Great message to end it on. And we'll end the podcast there. Thank you so much, Suyash, for coming on. Absolutely fascinating conversation. And if the listeners interested in finding more about Suyash's work, we'll put links to all of the relevant materials in the show notes. And we'll see you all next time for some more awesome computer science research.